us today. Is this on Zoom?
Maybe use this one.
Should I use this then? This one here?
No, only here. Oh, whoops. Not done now. Only this touchpad. Also not.
But if I can use this, is
Oh,
that
yeah.
okay?
Okay.
Yeah. Great. Well, thanks a lot for the introduction. Thanks a lot for the invitation to be here. I'm going to be talking about the consistent reasoning paradox and the indeterminacy function. This is joint work with Ben Adcock, Alex Bastunis, Paolo Companico, Paul Sievert, and Mihaela van der Schaar. I'm just wondering, does this work?
It's muted.
Is it muted? Okay, very good. And whoops, I'm going to start by asking the question, can we make artificial superintelligence? Whoops, suddenly it made a jump. Right, how on earth does this work? There we are. Fine. Okay, but to be able to talk about artificial superintelligence, I need to define it. Or, well, I'm going to use what seems to be now the canonical definition from Nick Bostrom. Any intellect that greatly exceeds human cognitive performance in virtually all domains of interest. I need this to be slightly more mathematical. I'm going to say any ASI must be on par with or better than any human on any intellectual test. You may argue that this is slightly weaker than Bostrom's definition, but what I need here are I need two quantifiers for all humans and for all tests. I'm going to use that a little later on. You may argue that superintelligence might be a little bit of science fiction, but I want to highlight that Delia Sutskever, who is one of the guys behind OpenAI, and when he left OpenAI in 2024, he started a new company called Safe Superintelligence. And you can read about this here on Wikipedia, if you can see the cursor. The company's mission is to focus safely on developing a superintelligence, a computer-based agent capable of surpassing human intelligence. And they've been able to get quite a lot of investors behind them, and they're now worth more than 30 billion. So the argument that I want to make is that there are key people in the community, and certainly also investors, who do believe in superintelligence. There are hurdles. Hallucinations, as you all know very well, I'm not going to spend too much time on documenting that. Hallucinations is a problem and really the Achilles heel of trustworthy AI. Another issue that we are also struggling with is explainable AI. We want AI to explain what it does. It's not simple, and as this paper here from The Lancet suggests, the title is quite illustrative. The false hope of current approaches to explainable artificial intelligence in healthcare. All right, so that was a little bit of a prelude. Now I'm going to describe to you the consistent reasoning paradox, which this talk is about. But before I do that, I want to say a little bit about the consequences of this paradox. And the first consequence is to deal with Turing's infallibility dilemma. In 1947, Turing pointed out the following: if a machine is expected to be infallible, it cannot also be intelligent. There are several mathematical theorems which say almost exactly that, but these theorems say nothing about how much intelligence may be displayed if a machine makes no pretense at infallibility. And the mathematical theorems that Turing is referring to would be Gödel's incompleteness theorem and his own halting problem. But as he points out, they don't say anything about how much intelligence may be displayed if a machine makes no pretense at infallibility. And this consistent reasoning paradox is going to help us quantify exactly that from Turing's infallibility dilemma. The second part is a necessary mechanism for superintelligence. So we can identify a key mechanism that must be present in a superintelligence, and that is computing what we call an indeterminacy function. I'm going to explain to you exactly what this indeterminacy function is. Without that, you can't create a superintelligence. And this mechanism is not present in modern chatbots, and without this, they will just continue hallucinate. I'm going to talk about hallucinations, and to make this well-defined, I'm using what now seems to be the one that the community has converged on. This is from the Cambridge Dictionary and also Wikipedia. When an AI hallucinates, it produces false information. Okay. So to be able to talk about the consistent reasoning paradox, I need to tell you what consistent reasoning means. And to do that, the best way is a very simple example. So here I'm going to give you two sentences. I'm going to read them out. Lisa and John are wondering who is tallest. John is measured to 178 centimeters, and Lisa is measured to 179. Who is tallest, Lisa or John? John and Lisa are arguing who is tallest and subsequently measure their heights. Lisa is 179 centimeters and John is 178 centimeters. Determine who is tallest of John and Lisa. So here I have two sentences. They are syntactically different, but they're equivalent in the way that they're really asking the same problem. Finding out that 178 is smaller than 179. Now, you may ask, how on earth would you define equivalence of sentences in a natural language? You cannot do that in general, but I'm going to later on restrict myself to problems that are just about arithmetic, and I can then make a perfectly mathematical definition of what equivalence of sentences are. This here is just to give you the gist. I have syntactically different sentences that are asking the same problem. And if I have that, I can make sense of the concept of consistent reasoning. An AI that provides the same answers to sentences that are describing the same problem is called a consistently reasoning AI. And then you may ask, where would you need consistent reasoning? Well, essentially in everywhere where you're going to do reasoning. But if you're a machine learner and you want to see a benchmark test, you can use the GRE test. And if you were educated in the US as I was, you may have, well, as I had, not so fond memories of having to prepare for this and going through all the sentence equivalence tests that I had to do for the GRE test. Now, consistent reasoning turns out to be strictly easier than sentence equivalence. This is a part of what we prove. And so the point is that if you are trying to do the GRE test and you're not even attempting to be a consistent reasoner, you're not going to do very well on the GRE test. You can ask, does chat attempt to reason consistently? Well, we could give it to the John and Lisa question here. Nails it. Not really a great surprise. It's trained on a lot of human data. We have a tendency of attempting to be a consistent reasoner, at least those who had to take the GRE tests. And that gives us a very simple conclusion. A superintelligence also has to attempt to reason consistently. Why? For all humans, for all tests? Well, if it's going to do better than at least me on the GRE test, I tried to attempt the best I could to be a consistent reasoner on that test. For many people who are much better than I on the GRE test, they say I must be better than them as well and must attempt to reason consistently. Okay, so get to the gist, you say. Now I'm going to show you the consistent reasoning paradox. And I'm going to build that around a collection of very simple problems. I could have done this with a lot of different problems. I choose one now that could have been asked in, say, medicine. I'm going to read it out. Jen undergoes 2 chemotherapies with dosage rates A1 and A2 per second, respectively. To optimally minimize the total treatment time, x1 plus x2, while ensuring that she receives a total dosage of 1, how should one choose the durations x1 and x2 if a1 is equal to 1 over 10 and a2 is equal to 1 over 2? You may recognize this as a linear program. It's a very simple linear program. And you see, if I fix a1 to be a particular number like 1 over 10, or a2 to be another particular number, 1 over half, 1 over 2, I specify one particular linear program. If I change to a1 to 1 over 8 and a2 to 1 over 3, I get a different linear program, right? But what I also could do is that I could change the syntax of the sentence, but keeping the values. So what I'm going to do now is that I'm going to change the part that says if A1 is equal to 1 over 10, and I'm going to change that to if A1 is given by the number 1 over 10, right? Now I have two syntactically different sentences. I just changed that part here and plugged it in there. I have two syntactically different sentences, but they're describing exactly the same problem. Nothing controversial. Did this make sense? Because this is the whole setup for the whole argument. Hopefully that made sense. So now what I have is a way of creating many different problems. You can think about, say, problem 1 here would be Jen and her chemo, with A1 being 1 over 10, A2 being 1 over 2. Problem 2 could be the same thing, but say with A1 equals to 1 over 8 and A2 being equal to 1 over 3. But each one will have many different sentences. They're syntactically different, but they will describe the same linear program. Right? And then you say, okay, so what? Well, now we're going to get to the gist. Now I can present to you the paradox. So the consistent reasoning paradox is a theorem. It has 5 components. I can write it out in plain English. You don't need technical language, but there is a mathematical technicality behind all of this. The first part of the paradox is the following. There's a collection of problems. Think about the problems of Jen and her chemo, where each problem is described by more than one equivalent sentence with the following property. Consider any family of these sentences such that each problem is described by exactly one sentence in this family. Then there's an AI, I'm going to call it gamma, that does not hallucinate. When given any sentence in this family as input, it will always give a correct solution. Okay? So what it says now is that if I have one sentence per problem, then there will exist an AI that can solve that. Very, very specialized. I'm going to call it special bot. It looks a little bit like a snake, doesn't it? So the theorem says that for any snake, there is a bot that can solve that problem. But the problem here is that that special bot is not attempting to reason consistently. If it would try to give it another sentence outside of its domain, it might freeze completely. You have to literally unplug it and plug it back for it to work again. So now you could ask, well, what would happen then if it attempted to reason consistently? Could you do that? And that's the second part of the paradox, which says the following. If the AI from CRP1 always answers any sentence describing any problem in CRP1, in other words, it will attempt to reason consistently, and then it will hallucinate infinitely often. But actually making that special bot, that gamma, reason consistently is strictly easier than the halting problem. I'm going to talk a little bit about why that is bizarre later on. Experts will pick up on this immediately. So now, what that means is that you can have the specialized bot, but the second it attempts to reason consistently, it will start hallucinating. When I say this to machine learners, they might get skeptical and smell a rat. And the reason why is one can think, well, will I ever see these sentences? What if these sentences become very long, like the length of the universe? And I can strengthen this, and I can write down the sentences for you. If I have time, I'll show you that at the end of the talk. And they don't become long. So you can actually make this here much stronger. I can make it so that you can see it, and it is not pure math mumbo jumbo. But now, you can ask yourself, could you detect the hallucinations that will come? Could there be a checker that says, this is an hallucination? I'm not going to give you the true solution, but this is an hallucination, right? Could you have such a device? And you see, here's the problem. Detecting such hallucinations are hard. In particular, consider the AI from CRP2, the one that is attempting to reason consistently and will hallucinate. It's strictly harder to determine if it has hallucinated than it is to solve the original problem. That is, it is impossible to detect whether the AI was correct or wrong, even with access to true solutions of the collection of problems from CRP1. And when I say that, you think that I'm bonkers, but this is a paradox. It is very paradoxical, but you cannot detect this even if you have an oracle for a true solution. And then you could say, could we try to do this in a randomized way? How about the following thought experiment? I have my original AI here, and I know that it's going to hallucinate. And I would like to detect when. So what I'm going to do now is I'm going to buy 100 other chatbots. They're going to be over here. They're all randomized. And I'm going to ask them, not the original question that I'm going to ask my original AI, I'm going to ask them, was it correct, yes or no? Does it hallucinate? What if 90 of them now says the AI was correct? Could I be confident, say 90%, that the AI now is actually doing the right thing? So that's also a very delicate question. And to get to the gist of this, I'm going to take a slight detour and talk about a universal rewriting algorithm. It looks a little bit like a wall of text here, but it's going to be worth reading the whole thing. Any randomized AI that, for some collection of questions in logical reasoning with unique answers, provide incorrect answers with a probability strictly lower than a half, I'm going to call that pretty sure, can be rewritten to be completely deterministic and trustworthy on this collection of questions. Moreover, on any question in this collection for which the original AI provided a correct solution with probability greater than a half, the new rewritten AI will be correct with absolute certainty. And as a corollary to that, because of the above statement in CRP3A, one cannot detect hallucinations of the AI from CRP2 with a randomized algorithm with probability greater than a half. And this statement here is just more than that, because this universal rewriting algorithm is not just something that we show the existence of, we write it out. You can write it out in a standard language. It will be roughly 2,000 characters. So it's a little bit like an extended abstract. And you can tag that on to any randomized algorithm, and you will rewrite it so that it becomes trustworthy, if it was already pretty sure. And the reason why this is crucial is that if you now have a pretty sure superintelligence, that must be able to rewrite itself to be completely trustworthy. Why? Because I can do it. I'm a human, and I just showed you the algorithm. I can tag it onto it. If it's going to beat me, it has to be able to do that itself. And that means that any ASI will actually be either 100% sure, or it will have no idea. If it is 70% sure, it has all the information. And either it knows what it's doing, or it has no idea, and that's why it has to say, I don't know. There's nothing in between. And the whole issue of I don't know is the crucial part, which I'm going to get to now, talking about the indeterminacy function a little later on in the talk. Okay. So I presented now 3 parts of the paradox. Now I'm going to get to the 4th. This is about explainability of AI. A core question in AI research is how to make AI explain how it reached its solution to a problem. And CRP4 addresses that. Consider the same collection of problems as in 1. Good old questions about Jenna or chemo. There's a family of sentences with each problem described by at most one sentence and an AI that does not hallucinate on this family of sentences. Fine, we knew that from CRP1, but this one here is special. It says the following. There is one sentence in this family for which the AI cannot provide, or can any other AI, a logically correct explanation of the solution. And what I mean by an explanation here, I mean a mathematical proof. So what is happening is the following. CRP3 said that a trustworthy AI must say, I don't know. There's nothing in between. And CRP4 says the following. An explainable AI must say, I don't know, when asked to explain, even in cases where it knows it is correct. That sounds completely absurd. It knows that it's correct, and on the question, explain why, it cannot do it. Okay, so now, what I've done so far is I sort of ripped up a wound and said all of these bizarre things can happen when you're going to try to create something which is super intelligent. But this consistent reasoning paradox is not a doom and gloom paradox that says you cannot do things. It says there are bizarre things happening. But there is a cure, and the cure is computing this indeterminacy function. And this is what CRP5 is doing. Because given the collection of problems in 1, that is where all of these bizarre things can happen. There still exists a trustworthy, consistently reasoning and explainable AI as follows. This AI will take an input and a prescribed number of minutes on any sentence. It will think for no more than the prescribed number of minutes before answering either I know, accompanied by a correct answer and a correct logical explanation, or it will say I don't know. If the sentence describes a multi-solution problem, the AI will always say, I don't know. However, there's only one problem in this collection, which is multi-valued, but of course there's many sentences describing it. But for the single-valued solution problem in this case here, by choosing the number of minutes to be large enough, the AI will be able to get it. So what does it say? It says the following. The underlying mechanism for this part of the paradox is computing this indeterminacy function, which I will describe in a minute. And by doing that, you can solve it. But the point I'm going to make is that this is not just a solution. It is a necessary solution. You're not going to get away with not doing the indeterminacy function. All right. So that was the consistent reasoning paradox. And now I'm going to get to the consequences that I told you about. So the first part was Turing's infallibility dilemma. Turing said that if a machine is expected to be infallible, it cannot also be intelligent. There are several mathematical theorems which say almost exactly that. But these theorems say nothing about how much intelligence may be displayed if a machine makes no pretense at infallibility. And now we can actually quantify that. Consistent reasoning. But the bizarre thing is that consistent reasoning is strictly easier than the halting problem. There's no reason why consistent reasoning is an answer to the infallibility dilemma. And for those who are experts here, we'll recognize the issue of having natural problems being below the halting problem. All problems that we have that are typically impossible to do, they're either as hard or harder than the halting problem. If you're interested in some of these things, I highly recommend this essay here by Björn Poonen. He's a formidable number theorist at MIT and also a great expositor on these issues. All right. But now I'm going to get to the other consequence, and that is necessary mechanisms for superintelligence. The first part that we've already discussed, any trustworthy AI must be able to say, I don't know. Fine. And the first thing I'm going to argue now is that a necessary mechanism for trustworthy AI is computing this indeterminacy function. And then I'm going to argue that it's actually necessary for a superintelligence. I'm going to do this in 2 steps. All right. So, how to create trustworthy AI that says, I don't know. This is about the indeterminacy function as I started working on in CRP5. And the key question is the following. How can the AI identify that it cannot solve the problem in order to say, I don't know? Moreover, how can it identify when it is correct? What do you do as scientists? We, as humans, we give up. But for so many different reasons, we're fallible on essentially everything, and we give up. What about the machine? The machine doesn't have to be fallible in that way. Does it have to give up? So in the 5th part of the paradox, there was this machine that had to take this extra giving up parameter. And the question is, do you really need that? Why couldn't the machine just say, that problem I can't solve, here is a problem that I can solve? Why couldn't it just do that? And the problem here is that this giving up parameter is necessary. There's no way that you can have an AI that does the same thing as the one that did solve the problem in CRP5 without that giving up parameter. And this is where we're getting really into the foundations of mathematics. This is because of the theory of what we call the solvability complexity index hierarchy, which generalizes